Hello, everyone. My name is Paweł Jurczenko, and today I will be talking about multi-threading on JVM platform. A quick info about myself. I work as a senior software engineer at Allegro, which is the biggest Polish e-commerce platform. At the moment, we have around 1,000 microservices. Most of them, like 90%, are JVM ones. Usually they are Java ones, then they are Kotlin ones, and then they are Scala ones. And Scala is the language I have been using for the last 5 years now, professionally. Things I'm interested in are distributed systems, concurrent computing, and functional programming. How will this presentation look like? Well, the presentation will have 7 different sections. And my purpose today is to show you a wide range of many different aspects when it comes to a multi-threaded JVM application. We will not have time to go into details in any of these sections. However, if you'll have any questions, feel free to ask them and I will try to answer them. Let's start by saying, how can we think about multi-threaded applications in the first place? And the way I like to think about them is to visualize them as a layered architecture, where we have a couple of layers, and each layer is built on top of abstractions that are provided by the layer that is directly below. Okay, and on each of these layers, we have a concept of a thread, which depending on the layer will mean something slightly different, but we'll get to that. At the bottom of this hierarchy, we have a physical hardware layer, where a thread is not a concrete abstraction, but more of an ability to perform a sequence of instructions. A layer that is built on top of hardware physical layer is called an operating system layer, where a thread is a concrete abstraction that we can manipulate on, or we can have references to. The next layer, the layer that is built on top of operating system layer, is called an application layer. And in case of JVM platform, it's a layer of JVM threads. If on the layer of JVM threads, we create another multi-threading abstraction, we call this layer a layer of green threads. And basically nothing stops us from going further into this hierarchy and create our own custom layer of multi-threading, as long as we have a use case for that, of course. There are also 2 terms that are very related to this hierarchy. The first one is called scheduling. And scheduling is basically a process of executing threads from the higher layers on threads that are placed directly below that layer. Okay, and we have two main types of scheduling. The first one is called preemptive scheduling, where the scheduler is in the full control of who executes when. And in the second type, the cooperative scheduling, it's quite the opposite. It's where the thread is in the control. It's where the thread decides about stopping its own execution and giving control back to the scheduler. The second term is called threading model. Okay, and the threading model describes the relation between neighboring layers. Okay, and we have 3 main types of threading models. The first one is called one-to-one, which means that each thread on the higher layer will have its counterpart in the layer below. In case of JVM platform, this is the relation we have between JVM threads and operating system threads, which means that if we create 10 JVM threads, we will also create 10 operating system threads. The next threading model is called M2N, which means that M threads from the higher layer will be executed on N threads from the layer below. And this is the relation we usually have when it comes to green threads, and not only on JVM platform. However, on the JVM platform, this means that we can have, for example, 1 million green threads running on top of 10 JVM threads. And the third model is called M2-1, which means that M threads from the higher layer will be multiplexed and executed on a single thread from the layer below. And this is the model that you can usually find outside of the JVM, especially in platforms that don't have native support for multi-threading. Green threads allow us to create such multi-threading abstraction on top of platforms that don't have native support for multi-threading. And let's stick to these green threads I have just told you about. Okay, what are they like in general? Well, they are threads like regular ones. However, they are not managed. They are not managed at the kernel space, but they are managed in the user space instead. In other words, this means that they are not managed by operating system, but they are managed at the application level in some way. They are scheduled by runtime library in the language we're using, or a virtual machine of the language that we have. Okay, and examples of green threads you could heard of are coroutines, which we have implemented in Kotlin, are Go routines, which we have in Go, and fibers, which have many different implementations in many different languages, and we'll get to fibers later. Okay, so what is the reason of having green threads in the first place? Well, the main reason is that we would like to have lower costs of thread management, lower than in the regular JVM threads. Okay, we would also like to have more efficient usage of resources in the machine that we'll be using. Okay, we'd also like to have a different semantics when it comes to blocking, because we would like to be blocking at the level of a green thread in a way that doesn't propagate this blocking as a blocking of the JVM thread in any way. Okay, and because green threads are more lightweight abstraction, like significantly more lightweight abstraction than regular JVM threads, they can be created in thousands or millions in a single regular application. And as I said, if we have a platform that doesn't have native support for multithreading, we can create one by using green threads. Okay, when it comes to concrete implementation of green threads, there are many of them in many different languages. We will not have time to compare the implementations. However, the idea remains the same, okay? The main idea behind them is the same. They differ in implementation details, okay? Some languages have decided that green threads should be the main threading model used in the language itself, okay? And this is what happened in Go, where we have Go routines. This is what happened in Haskell, where we have Haskell threads. And this is also what happened in Erlang, where we have Erlang processes. And they are called processes and not threads because they don't share memory. Okay, instead they communicate solely by message passing. In case of the JVM platform, we have two types of solutions: the solutions that we already have, or the solutions that we will have in a foreseeable future. Okay, and for example, in case of coroutines, we already have an implementation in Kotlin. When it comes to fibers, we already have an implementation in Java, which is Project Quasar, which is available for a couple of years now. And in case of Scala, we also have a couple of fibers implementations, for example, in Monix, Zio, or Cats Effect. When it comes to future solutions on the JVM, we will have Project Loom, which will provide or bring a native support for continuations, coroutines, and fibers on the JVM platform itself. But this is the matter of the future. It's currently in the development process. Okay, what else do we gain by using green threads? Well, it turns out that we can rethink or redesign the way we've been using concurrency primitives in a way that we will achieve a different semantics when it comes to blocking, because we would be able to block at the level of a green thread and not at the level of the JVM thread. So for example, in case of locks and semaphores that traditionally are like blocking abstractions, they will still be blocking. However, they will be blocking at the level of a green thread. And this blocking will not propagate as blocking of a regular JVM thread. And let's see an example of that. In this example, I'm using like a traditional Java concurrency data structure, which is called array blocking queue. And let's see what happens when you try to put an element into the queue when the queue is full, okay? So the API of this data structure allows us to do this in one of three ways. The first one is method add, which unfortunately throws an exception when the queue is full. The second option we have is method offer, which will return a flag, false. The element wasn't added. And the third one will block the JVM thread until there's space in the queue. As we can see, none of these solutions is perfect. All of them have some kind of a problem with itself. Okay, can we do better than that? Well, I believe we can. However, we would have to use a different data structure here, a data structure that is not based directly on JVM threads, but it's based on green threads instead. And for this purpose, I'm using Monix library here and one of its data structures, which is called concurrent queue. So we create a concurrent queue, and we try to put an element into the queue in an asynchronous way. We have two possibilities here. The first possibility is that there's space in the queue, so the element will be added and the operation will succeed, the future will be succeeded. The second possibility we have is the case when the queue is full. What happens now? Well, it turns out that the fiber we were running on will be suspended. The thread that the fiber was running on, the JVM thread, will be released to the thread pool, and we will start asynchronous and non-blocking waiting until there's space in the queue again. And at some later point in time, when there is a space in the queue again, the fiber we were running on will be awakened, some thread will be assigned to the fiber, and the operation will be able to be performed, and the future will succeed. All of that, including the waiting for the space in the queue, will be asynchronous and non-blocking. No JVM blocking will happen in the process. Okay, and I would like to stick in the world of non-blocking APIs, non-blocking IO operations in general. Okay, but before that, we have to ask ourselves, what is the problem with blocking IO operations in the first place? And one of the problems is that very often when we have a lot of blocking IO operations in our application, we also have many JVM threads in such application. And this is a problem, and there are many reasons for that. Okay, the main one, like the most obvious one, is that we will have high memory consumption. A single JVM thread will, by default, require 1 megabyte of memory. Okay, so by having 1,000 threads in the JVM application, we will require 1 gigabyte of memory just for the fact of maintaining so many threads in the application. The next problem is that if we'll have many JVM threads, we will also have many context switches. And if we have many context switches, then we will pay the price just for the fact of constantly switching the context. The next problem is that if we have CPU-bound operations in our system, then constantly switching the context will decrease the throughput of such operations. CPU-bound operations don't like context switching. Okay, the next problem is that if we have a lot of context switches, then we will also constantly clear and populate cache values. Effectively, such application will work in a way that there's no caching at all. But in reality, it might work even worse, because we'll have to pay the price just for the fact of constantly clearing and populating cache values. The next problem is that every thread on the JVM is also a GC root, which means that if we have a large number of JVM threads, we might significantly increase the time of garbage collection process. We also have to demystify one myth here, okay? Myth related to non-blocking IO operations in general. Okay, so there's a myth that non-blocking IO operations are about better performance of IO applications themselves, which is not the case. And there are two reasons for that. The first one comes from physics. Let's assume that we would like to send 1 gigabyte of data over the network. So regardless of the API we'll be using, blocking or non-blocking, the operation has to be performed in a physical sense, okay? All of the bits from that 1 gigabyte of data have to be converted into an electrical signal and have to be transferred over the wire, okay? The type of the API doesn't change that behavior, right? The second reason is that at the lowest level, IO operations are already asynchronous and non-blocking because they are using CPU interrupts. So we can see that non-blocking IO operations are not about better performance of IO applications themselves. Instead, they are about better or more efficient resources usage. And if we have more efficient resources usage, then it also means that it's possible that we will have better performance of the application in general. But this will be an indirect consequence of using non-blocking APIs, and the direct consequence will be more efficient resources usage. When it comes to concrete types of external communications, in case of network IO operations and performing them in a non-blocking manner, we don't have a problem usually, because this is well supported by operating systems. This is well supported by the JVM itself. We also have many non-blocking HTTP clients, For example, we have Async HTTP client, which is quite popular in the world of Scala, I would say. In the world of Java, we have Spring Web Client, and since JDK 11, we also have a non-blocking HTTP client that is part of the JDK itself. So usually not a problem. It's not a problem to perform network calls in a non-blocking manner. The problem starts when we like to have a non-blocking communication with file systems, okay? And the problem is that not all operating systems support non-blocking file system operations well. And unfortunately, Linux is one of them. Linux doesn't have full support for non-blocking file system operations, which means that effectively JVM running on Linux doesn't have non-blocking file system operations. And nothing is changed by Java new IO package here, because even though we have classes like asynchronous file channel, they are asynchronous as the name suggests, but they are blocking. A thread pool is used under the hood anyway. Okay, and this problem affects not only JVM platform itself, it also affects other platforms. For example, it affects libuv library, which is library that is used and popular in the world of Node.js. It's also affected by this particular problem, and it also uses a thread pool when it comes to using to performing file system operations. All of the things I have said at the slide might change in the future. And one of the reasons is that last year, a new kernel module was introduced to Linux, and it's called IO-uring. And it's possible that this will change the way we perform non-blocking file system operations on the JVM. However, we will just have to wait and observe if something is changed in this manner. Okay, when it comes to performing a non-blocking communication with non-relational databases, we usually don't have a problem as well, because most mainstream non-relational databases have non-blocking clients to the databases. So for example, in case of MongoDB, we have Async driver. In case of Cassandra, we have DataStax Java driver. We have Lattice for Redis, and we have many, many more. So usually when it comes to non-relational databases, we don't have a problem with non-blocking communication. On the other hand, in the world of relational databases and communicating with relational databases in a non-blocking manner, there is a problem, okay? And the problem is named JDBC. And there are many problems with the JDBC itself. One of the problems is that it's quite old. It's 23 years old now. And the second problem is that its API is completely blocking. The API is also quite low level. There are many leaky abstractions, and the API, as you may guess, is quite Java-ish, I would say. There are many nulls, there are many exceptions, there are side effects, basically things that we functional programmers of Scala language usually don't like. Okay. However, if we forget about JDBC for a while, a couple of opportunities arise, especially if the databases that we're using are Postgres or MySQL, because we have both low-level and high-level solutions here. Okay, when it comes to low-level ones, they will usually be similar to JDBC itself, but they will be non-blocking instead. High-level solutions, on the other hand, will provide, for example, some kind of a DSL to express our communication with the database. And I would like to show you an example of that. In this example, I would like to show you how far with being non-blocking and reactive in our application we might be. And I think that we can go pretty far. Okay, in my company, the main abstraction that we're operating on is called an offer. You can think of an offer as a product, as a smartphone, as a book, as a ticket to a concert, all that kind of stuff. Okay, so let's assume that we have a relational database, a relational table, and in the table, we're storing information about the offers. Okay, and at application level, we would like to react each time a new offer is inserted into the database. What options do we have here? Well, the traditional approach here would be to just query the database and periodically ask the same question. Hey, have some new offers arrived to a table? However, sometimes we would like to react faster. Sometimes we would like to react just as soon as the offer is inserted into the database. So instead of such pull-based approach, we would be looking for a push-based approach instead. But is it possible to have a push-based approach when it comes to relational databases? And it turns out that yes, it's possible. What do we need here? Okay, we need 3 ingredients now. The first one would be to have a mechanism that will react to a change in the table. Okay, and we already have such mechanism in the world of relational databases, and it's called a trigger. Okay, so we will have a trigger that will react each time an offer is placed into the database. The second thing we need is a way to push the data somewhere from the database. Okay, and it's also possible when it comes to relational databases. In case of PostgreSQL, we have a concept of a channel. You can think of a channel as a queue. We can push the data onto the channel, and we can subscribe to the data at the other end of the channel. Okay, so now we have 2 ingredients out of 3. Okay, so we have a trigger that will react to a change in the database. The trigger will call a function. The function will push the data onto the channel. And the third ingredient we're missing here is consuming the data, consuming the channel. And we would like to do this at the application level. However, how can we subscribe to such channel in the world of Scala code? Okay, and for this purpose, I'm using a skunk library here. Okay, skunk is still in the development process. However, it will provide, or already provides, out of the box support for PostgreSQL channels. Okay, so I create a regular database session here, and as soon as I have a session, I'm saying that, okay, I'm interested in communication with a channel called offers. Then I say that I would like to listen to the channel. Nothing is executed yet, of course, because everything is evaluated lazily. At this point, skunk returns me a FS2 stream, a stream of notifications coming from the database, pushed to me by the database. And since in my company, we interoperate with Java and Kotlin code as well, I'm also showing you how can we go from one stream processing implementation to another. In this case, I'm going from FS2 stream to Project Reactor's Flux. Okay, and this is possible thanks to Reactive Streams Protocol. This way, this code might be consumed by Kotlin or Java code now. Okay. And if there are, of course, nothing happens until we subscribe to the stream. The stream might be also infinite, okay? And when there's no data in the channel, we will not be blocking any JVM thread. All of the waiting for the data will be executed in an asynchronous and non-blocking way. So as you can see, we can go pretty far when it comes to having a non-blocking reactive application, and relational databases doesn't have to stop us from going fully reactive. Okay, there are also some attempts to provide generic solutions to non-blocking communication with relational databases. There are 2 main approaches, I would say. One of them was called ADBA, and it was developed by Oracle. It was supposed to be an extension of the JDBC that would introduce some asynchronous capabilities. However, in the September of 2019, Oracle decided that they will no longer be developing the solution. Instead, Oracle said that they will wait until Project Loom is released, and as soon as Project Loom is released, JDBC will be based on fibers and not directly on JVM threads, which means that if we'll perform a database call using JDBC, the call will be blocking, but it will be blocking at the level of a fiber, and this blocking will not propagate as blocking of a JVM thread. The second solution here is the one that was initiated by Pivotal, which is a company behind Spring. The API is based on Project Reactor, which means that we will have Mono and Flux in the API, and the design and the API of the library will be compliant with Reactive Streams Protocol, which means that we, Scala developers, don't have to use project reactor in our code base. We can go from mono or flux into Monix observable, for example, or FS2 stream, thanks to reactive streams protocol, basically in the opposite direction to the one I have shown you in the previous slide. Okay, and this is all when it comes to this section of non-blocking APIs, non-blocking IO operations. Now I would like to tell you more about thread pools in general. Okay, how many thread pools should we have? What types of thread pools? How many threads should we have in the thread pools? I'd like to start by answering a question. Is it good to import Scala's global thread pool across our code base? Okay, so it turns out that many applications already do that. Many companies already do that. Okay, so they have like only Scala global thread pool and they're importing it everywhere in the code. And both applications and both companies are doing fine. Okay, and the reason is that, let's be honest, not all applications out there, including many my applications, don't require high performance, low latency, high throughput. Okay. However, if we have such strong performance requirements, then importing Scala's global thread pool across our whole code base will just not be enough. What options do we have here? Well, a good rule of thumb here is to have at least 3 different thread pools. The first one will be used for CPU-bound tasks. The second one will be used for blocking I/O tasks. And the third one will be used for non-blocking I/O tasks. What is the reason of such separation? Well, the reason is that this way, all these different types of operations might be executed independently. They will not have to compete over the exact same threads, okay? Because they will be running on different thread pools instead, okay? Effectively, they will be scheduled independently by the operating system, and they will not be scheduled by the application or the JVM itself. When it comes to concrete types of thread pools and numbers of threads, in case of CPU-bound operations, you should be careful with using fork join pool, especially when you're having long-running CPU-bound operations in your application. And the reason is that in such case, the thread pool might think that instead of a long-running CPU operation, you're performing a blocking I/O operation. And in reaction to that, the thread pool might add more threads to the thread pool itself, which, as I said at the beginning, is a problem for CPU-bound operations. It will decrease the throughput of such operations. CPU-bound operations don't like context switches and having many threads. Okay, instead, we can use a regular bounded pool. Okay, for example, fixed thread pool, when we explicitly set the upper bound of the threads in the thread pool. Okay, and you also have to remember to have at least as many threads in the thread pool as many CPU cores you have in your machine, because otherwise you risk underutilizing the available resources. In case of blocking I/O operations, a good rule of thumb here is to have an unbounded pool, unbounded at least at the level of the thread pool itself. Instead, we'll provide limits at the higher semantic level, okay? And I will show you an example of that. By higher semantic level, I mean things like HTTP clients, database clients, HTTP server configuration, all that kind of stuff. And the third pool is a pool for non-blocking I/O operations. And it's also, it also might be like a regular bounded pool, for example, fixed thread pool. It might be a small one, okay? 1 or 2 threads should be enough. Or if you have, for example, 4 cores, you can have a single thread for a single core, okay? And the thread pool will work solely as a dispatcher. It will listen to notifications coming from the operating system. And as soon as the notification from the operating system arrives, it will shift the execution to one of these 2 other thread pools, okay? Effectively, this pool will work in an event loop manner, okay? We have to remember, though, that we shouldn't be performing any CPU-bound operations here or any blocking I/O operations, because this is not the responsibility of the thread pool, okay? Its only responsibility is to listen for the notifications coming from the operating system. And I would like to show you an example of using the unbounded pool in the in the blocking IO scenario. Okay, so let's assume that we have 3 different types of blocking IO operations in our system. Okay, and the first one is blocking network calls. The second one is blocking database calls. And the third one is blocking file system operations. All of these operations underneath will use the exact same thread pool, cached thread pool, which is unbounded by design. Okay, and instead of limiting the thread pool itself, we'll provide limits at the higher semantic level. So for example, at the level of HTTP client, we can say that we would like to have at most 50 simultaneous HTTP requests. The same goes with database client. We can say that we would like to have at most 10 simultaneous database operations. And the same goes with blocking file system operations, when we can say that we would like to have at most 20 file system operations at the same time. Okay, what did we gain here? Well, we gained 2 things here. The first one is that we effectively, by providing these higher level limits, we limited the thread pool to 80 threads in total. Okay, and we didn't have to think about the exact number. We didn't have to think about the 80. We didn't have to calculate it. We didn't have to set it at the level of the thread pool itself. Instead, we only had to think about those higher level limits. The second thing we gained here is that because the thread pool is cached, it means that a thread, after finishing its execution, is not yet killed. Okay, it might be reused for other type of operation. So for example, if we have a blocking network call, and the blocking network call is finished, the thread might be immediately reused to perform a blocking database call. Effectively, we're promoting reusing threads in our application instead of constantly killing and creating them, which in general should result in a better overall performance. Okay, and in the next section, I would like to continue giving you some good or best practices when it comes to multi-threading in general, not only when it comes to thread pools. Okay, so first of all, the main one, you should avoid concurrency for as long as possible. Okay, so if we have 2 solutions to a problem, both of the solutions satisfy you, and one of them uses concurrency and the second doesn't, in general, you should prefer the one that doesn't use concurrency, and you'll thank yourself later. Okay. The next one is that if we have 2 solutions and both of them satisfy you, and one of them uses low-level concurrency and the other is using high-level concurrency, in general, you should prefer the high-level solution. And the reason is that usually they will hide some implementation details. Usually they will be easier to understand, to maintain, and in general to operate. Okay, the next one is that you should choose your concurrency primitives carefully. We have many different concurrency primitives, and some of them might fit to a problem better than the other ones. And unfortunately, we have a problem in Scala ecosystem with this rule, because we have a problem of overusing akka actors. Akka actors are a great abstraction. Akka library itself is a great library. However, they are not silver bullets. Okay, for some problems, akka actors will in fact be the best possible solutions, but for for other problems, other concurrency primitives might fit significantly better than akka actors. The next thing is that you should know your thread pools. You should know how many thread pools you create. You should know how many thread pools external libraries create. You should know how many threads you will have, how many threads might be created by these external libraries. All of that is important for the production use of your application, because otherwise you lose predictability. You lose confidence about how the application will behave when bad things start to happen, okay? And I will show an example of that. Some time ago, I was performing some HTTP calls to many microservices in my company. I have used a blocking OKHTTP client, and I said that, okay, I would like to have at most 100 simultaneous HTTP requests. And my assumption was that in the runtime, I would be having around 100 threads. just for the fact of performing such HTTP communication. However, after running Visual VM, it turned out that I have 134 threads in my application. Okay, spoiler alert, 14 are completely unrelated to the HTTP communication, but it still left me with 120 instead of 100. And after going through the documentation of OKHTTP, I haven't found anything. After going through the code of the OKHTTP itself, I haven't found anything. Okay, so I lost predictability about my application. I lost the confidence. I wasn't sure if I can go into with this solution into production. Okay, which is a problem in general, right? And we'll get to the example in a moment as well. If you're using external libraries that create thread pools, you should prefer the ones that allow you to plug your own thread pools, because this way you have the control over the runtime over the runtime characteristics of your application. If you can't plug your own thread pool, you should at least be able to configure it like extensively, at least when it comes to the upper bound of number of threads that might be created by this external library. And fortunately, OKHTTP allows us to do that. It allows us to plug our own thread pool, which is what I'm doing here. Okay, so basically I'm creating my own thread pool, which is bounded, fixed one, 100 threads that will be used solely for the purpose of HTTP communication. And in Visual VM, I have 114 threads. 14 are completely unrelated to the HTTP communication, and 100 is used solely for the fact of HTTP communication. And I have confidence. This way, I got my confidence back. This way, I got my predictability back. Okay. At this point, I know the runtime characteristics of my application, and I can go to production without having worries about my application. And the last one in this section, if you're using the following expression in your code, which is runtime get runtime available processors, or the external library that you're using is based somehow on this expression, you should be careful, okay? Because it's not 100% reliable when it comes to virtualized environments. For example, you can have 4 CPU cores in your environment, and this expression might, for some reason, return number 1 and not number 4, okay? Which is possible. It happens. By the way, the number 1 is the lowest possible outcome of this expression. However, even if the number 1 is correct, then it's also quite risky to have a thread pool with a single thread only, because you might encounter some trivial deadlocks. Okay, what can we do about it? How can we solve the problem? Well, we can just make sure that whatever is returned by the expression, we will have some guard, okay, that will ensure that we have for at least as many threads, for example, as we'd like to have. In this example, I'm making sure that I will have at least 2 threads in my thread pool. Okay, you can go with 4 here or 8 here, depending on your use case. But you just have to be, you just have to guard against returning 1 by this particular expression. And in the last section of my presentation, I would like to tell you something more about asynchronous stack traces on the JVM platform. Okay, first of all, I would like to show you an example that will show us that there is a problem with asynchronous stack traces on the JVM. In this example, I have 2 asynchronous methods. One is method foo, which will asynchronously call another asynchronous method, which is called method bar. And in the bar method, for some reason, fails with an exception. And in the main method, I'm waiting for the result of those 2 asynchronous calls. And what stack trace did I got here? Okay, so the stack trace was pretty regular one. The message was correct. The exception type was correct. The method bar was there. However, there's one thing missing here. And the thing that is missing is method foo. It's nowhere in the stack trace, unfortunately. So, sorry. So we lost important or valuable context information, even though the code was like the simplest possible one. So you can imagine how many valuable or important context informations do we lose by having complex asynchronous logics. Can we do something about it? Well, there are a couple of attempts on the JVM to solve this problem in many different languages and in many different libraries. Some attempts try to solve the problem at the level of stream processing. For example, this is what happens in Project Reactor. Kotlin, on the other hand, tries to solve the problem at the level of coroutines. We also have some solutions provided by the IDEs. In this case, we have IntelliJ's async stacktraces. And we also have a solution in Scala world in the library called Zio, which many of you probably already know. Okay, and I would like to show you an example of such asynchronous stacktrace in Zio library. Even though I don't use Zio in my company, I don't use Zio in production, and I'm not planning on using Zio in the foreseeable future. However, I still think that this solution is quite interesting. And I hope that maybe other libraries in the Scala ecosystem will also try to address the problem of asynchronous stacktraces, and maybe all of these solutions will compete with each other. Okay, so this is basically the same code, but instead of using Scala's future, I'm using Zio's data structures here, which is basically a task in this particular case. What exception did I get here? Okay, the exception was like a regular standard one. The message was correct. The type of exception was correct. The method bar was there, and the method foo wasn't there. Okay, so the same problem we had. However, it turned out that it's not the only stack trace I got here. I also got a second stack trace which contains the method bar. We have this important, valuable information back in our stack trace. Okay, so how does it work? How does it happen that we have this second stack trace? Well, it turns out that in Zio, asynchronous operations are running on top of fibers. And when one fiber calls another fiber, it propagates some context information to that fiber. Effectively, in parallel to creating a regular thread level stack trace, we're creating a second fiber level stack trace. And when something bad happens, the two stack traces are combined and they are printed into the console, which leaves us with something along the lines of the code in the slide. Of course, in reality, the stack traces were longer, but the method foo was there. We were able to find the method foo somewhere in the stack traces. And this is all I have for today. If you'll have any questions, feel free to ask me. I will try to answer them. You can also feel free to contact me after the conference. You can find me on Twitter, or you can send me an email. Thanks. I will start by answering one of the questions from the Slack channel.
It's even better. So
okay, yeah, the question was about affinity pools. It came from Vladimir. Okay, so as a quick reminder, what are like affinity pools in general? Where they are thread pools that try or will try to perform your operations on the same thread. This might be especially useful when you have like long-running stateful operations, where sticking to a single thread will allow you to reuse the cache values that you were populating in the previous iterations of your execution. So in general, this should result in a better performance overall. In case of JVM platform, we have an implementation, for example, in Ekka, where we have a dispatcher called affinity pool. And this dispatcher will make sure or will try to perform your actor, a particular actor, always on the same thread. So if the actor is like a long-running stateful one, and the actor will be like pinned to a particular thread, then you will be able to reuse the cache values in that actor from the previous executions of the actor itself. So for example, if you're processing a lot of messages, then previous executions of the messages and cache values that were populating during the execution might be reused in the future executions of the actor. That's possible thanks to the affinity pool, which will try to always execute your actor on the same thread. You can go even further than that, and you can use a library that is called Java Affinity Threads. And this library allows you to acquire a single CPU thread just for yourself, or even acquire a single CPU core just for the thread of yours. And this way you can be sure that your computation is the only that will be executed on the CPU thread or the CPU core, and that no other operations will be scheduled on that thread pool. And this, of course, might be especially useful in like long-running stateful operations where you're looking for things like low latency or high throughput, and you really want to make sure that you're the only operation that has access to the CPU or a core.
Thank you. Thank you.
Thank you, Vladimir. It was a really good question, to be honest.
One more question. Could you share your experience with the garbage collecting in multi-threaded environments?
I haven't had much experience with like tuning garbage collection in multi-threaded applications. So like regular rules, I was following like regular rules here, and depending on the for example, heap size, I will be using like G1 garbage collection. We actually didn't have much problem with problems with garbage collections. So I wasn't like doing my experiments much with garbage collection in general.
Thank you.
Hi, Paweł. How are you? It was a great talk. I heard the recording because we spoke at the same time. But great talk. My question is about, I have two questions. The first is about the Loom project. Can you shed a little bit more light on it? You said it will support both coroutines and green threads at the same time. So how is that possible?
Yeah, well, basically the problem that Project Loom is trying to solve is to provide a native support for coroutines, like continuation, sorry. Okay, so this is something that we didn't have at the JVM platform, but Project Loom will try to provide like an abstraction of a continuation to the JVM platform. And if we have continuation and we combine the continuation with a thread pool, for example, then we already have a fiber. And this is also an abstraction that will be provided by the Project Loom. So Project Loom will basically provide two like abstractions: continuations on its own, and when you're a library creator, you could be using continuations like directly and operate on them directly. And the second abstraction that will be provided are fibers, which is basically a continuation or a set of continuations combined with a thread pool. Okay, so these are the abstractions that will be provided, and we will have native support for them at the JVM level. And when this happens, then fibers, the abstraction of fibers, will be working like regular threads. Okay, so your existing code will be able to work on top of fibers instead of JVM threads, and we'll be able to like be blocking on the level of a fiber and not be blocking at the level of the JVM thread. Does that answer your question, or you like to some more details?
I think so. So the continuation is the building block that everything will be happening about.
Yeah.
Great. So I use Zio in my day-to-day. You're probably using Monix, I understood.
Yeah.
I think it's probably similar in thread pooling. So it's obvious when to choose the blocking thread pool, right? But let's say you have tests that take a long time to finish calculation on a CPU. Will you stay on the default thread pool? Do you use spin up another thread pool with Monix? I mean, how do you do that specifically in a green thread environment?
Okay, so when I use Monix, I follow the rules I have shown in the slide. So usually I have three thread pools at least, and I'm using like Monix shift operators to go from one pool to another. So for example, when I have a long stream processing, and during the processing, I'm like hitting to PostgreSQL, sometimes to Mongo, sometimes to other database, or I'm performing HTTP call to external library, then I'm like switching threads all over again. So after like having a blocking call to the database, I'm instantly shifting my computations to like CPU thread. I'm performing some transformations in memory, so I'm using CPU thread then. And when I have to go, for example, to Mongo or to perform a non-blocking HTTP call, I'm shifting to another pool. So I'm constantly changing the threads. I'm constantly shifting the threads to change the thread pools I'm actually I'm currently on. So you were asking about long-running operations, I think.
I think you answered the question. One follow-up is, so when you switch it, it's on the call side, you don't actually see it, right? It's on the definition of the monad, let's say. Something like that.
Yeah. Well, I'm using things like dependency inversion principle and things like hexagonal architecture. So my infrastructure knows a lot about threads and not my domain necessarily. So my domain is like free of having to switch the thread pools to have a shift. I moved that problem to the outside of my main application, outside of my main code, and I'm switching the threads at the level of infrastructure. Okay, so for example, when I have an interface and the interface is implemented by Postgres implementation, then the Postgres implementation is aware that its own operations should be performed on a blocking thread pool because, for example, I'm using Duby library. Okay, and the same goes with like an interface to like some external microservice. The implementation will be non-blocking HTTP call, and the implementation itself in the infrastructure layer will be aware that it should be performing in a non-blocking way. So to summarize, the outside world of my main code, of my domain logic, is aware of the thread pools it should be executing itself. So I move the problem like to the outside of my main application. I move to the layer of infrastructure, and like hexagonal architecture helps me here basically.
And also the Monix library, because I think it's harder with implicit execution context in plain Scala. It's really hard to
exactly
to not see it. So
I know exactly what you mean, and yes, this is the case in Monix. Which in Monix it's much easier than with implicit execution context, because you don't have to jungle with the execution context. You don't have to pass it all over the place. You can just put the execution context at some point, and you can just move it as move the resulting observable, for example, or task. Just move the task itself around your application, not necessarily the accompanying execution context.
Great, thank you for your answer.
Thank you.
Listen, on your talk, I think maybe it's open idea. In computing, the 10 times difference between on performance, that 10 times penalty, is not something big. For example, Python is work 10 times slower than C, but nobody can. So the question is why nobody just ignore the penalty of having real threads and just spawn a thread for everything?
I'm not sure I understand the question. Are you asking about like using a thread per request model?
No, something like this, because because we know that concurrency is hard, yes, and we know that, for example, in the with having Python, for example, it's much slower than C, but nobody cares because the programming on Python is easy, yes. So I think why not exist programming technique, just ignore performance penalty and do all in real threads.
Okay, so like there are a couple of questions here, I believe. Well, the first thing is that you're asking about, you're telling that sometimes we just don't have to care about like the performance, and that's true. Like many applications out there don't require like high performance, high throughput, low latency, and that kind of stuff. So I know, for example, some applications that are using Python and they are doing completely fine because they don't have strong performance requirements. Okay. The next thing you've been mentioning is that I think that you've been mentioning is using like a request per thread model, and it's also like working to some degree. For example, in Spring, it was like pretty common to just have a separate thread for each separate request. However, and it works if you don't have like strong performance requirements. However, when things start to fall apart, and where for example, when you have like a lot of concurrent users, then this results in spawning like many threads. Okay, and as I said in the presentation, having many threads on the JVM is a problem. Okay, so you'll start having like a high memory consumption. You might encounter some problems with garbage collection. You might have problems with like context switching and decreasing your throughput. So it all depends on the characteristics of your application. Depends on what are you looking into in your application in general. If the performance is not the case, and maybe, I don't know, stability or like maintainability, then I wouldn't be worrying about performance much. I wouldn't be using Scala probably if the performance wouldn't be a necessity for me. However, since I work in a company that processes like a lot of data, a lot of requests, a lot of users concurrently, then I think that the JVM itself is a good platform for that. And in Scala, I also have like a lot of tools that allow me to express things like quite easily, and simultaneously the things will be performing really well, even under heavy load, which we encounter. We are an e-commerce platform, so we can imagine that we have like a lot of concurrent users at the moment due to coronavirus, and we also have like heavy loads during the winter, for example, and Christmas. So yeah, I don't know if that answers your questions. If that answer your question, but you can ask me something more if that's not the answer to your question.
Thanks. It was just an open idea, which.
Okay.
I have a question. Paweł, as far as I understood, you are working in e-commerce, yes?
Yeah.
Tell me, which particular applications requires multi-threading and heavy loads? Some use cases in e-commerce which require such solutions.
I don't think that e-commerce itself is the only business that requires like multi-threading and multi-threaded applications. The thing that matters here is like a number of users. Okay, so we're like the biggest Polish e-commerce platform, and in Poland we have 38 million people. So you can imagine that we have like many users of our platform. So there's a lot of load that has to be distributed. Of course, we distribute it in very different ways. Sometimes we distribute it at the level of like caches and like load balancers. Okay. Sometimes and this is the first level of like the distribution. But sometimes even after the initial distributions, your application there's a high load onto your application. And if that happens, then yeah, multi-threading is like the only way to go, I think. For example, if you have an application that receives like 15,000 simultaneous requests, then doing this in a like synchronous and single thread manner wouldn't be like possible, especially if you're having especially if you have to like communicate with other microservices at the same time, especially when you have to communicate with databases at the same time. So basically, there are many things combined here. First of all, a number of concurrent requests. This is the first problem. Second of all, since we are in the microservices world, you will be performing a lot of things in simultaneously. So you will be hitting to the database, you will be hitting to another service. So combining all of these, a multi-threaded application is the only answer, I think, because you just have so many things to do at the same time. And yeah, I don't know if that answers your question.
So the question was almost it. Okay. So your load is more like I/O bound. So you are using.
Yes, exactly. This is correct. Yeah. My applications are usually I/O bound because we're like communicating with databases and other microservices. So if we're I/O bound, then we will have a lot of thread pools, a lot of threads, a lot of context switching, etc. And CPU bound things also happen, but they are not so common as I/O bound things.
Okay, and thank you for your trick showing how to consume triggers from Postgre, and it's not blocking. Quite interesting idea. I never thought about it.
Thank you, thank you. I'm glad you enjoyed it.
It might be a question not about actually Scala, but do you use a lot of business logic inside of your Postgre?
Well, that's an interesting question because we had discussion in my team. How far should we go with expressing logic in our application, and how far we should go with expressing logic in like Postgres or in databases in general? And I think it's a hard question, and we haven't solved that yet. I think we try. The solution we're trying to do at the moment is, as long as we can, and as long the performance isn't like decreased, we try to perform as many things at the application level and not at the level of the Postgres. However, sometimes in such cases like the trigger ones, like the trigger is the only solution, so it has to be at the Postgres side. Okay, so as a rule of thumb, we try to express our logic at the application level, and sometimes when there's a significant reason not to do so, we express the logic in Postgres. And in general, we don't have much logic expressed in Postgres.
Okay.
And I'm also using, when it comes to expressing the queries itself, I'm using Duby library. So I'm like writing plain SQLs, which is a good thing, I think. I don't have to fight with the library. I was using Slick for a couple of years, and sometimes I was fighting with the library. Sometimes I was having problem to express my complex database call in the Slick DSL. However, I knew how to do it at the level of SQL, but I just couldn't express it in the language, in the library. So after going to Duby, all of the problems like were solved. All developers, basically, including junior developers or interns, know SQL, so they don't have much problems with writing SQL queries.
Do you have horizontal scaled Postgre cluster solutions?
Yeah, we have our Postgres are running in clusters. We have also 2 data centers, so we're having like a replication. We have a synchronous replication inside one data center and a synchronous application across the data centers. So yeah, our Postgres are running in clusters.
Thank you. Thank you.
Thank you.
Are you follow some other programming language than Scala?
Okay, I'm not following many programming languages at the moment outside of the Scala world. I think that so many things happen in Scala ecosystem that it's hard to follow many languages simultaneously, especially since I'm very interested in Scala itself. After like 5 years of programming, I'm still not tired of using Scala. Recently, I was working with some other teams in my company, and I was writing some Kotlin code. And I think it's a pretty good language, to be honest, especially if you're having a Java application at the moment, and for some reason you were afraid of going Scala, then Kotlin is like a good answer to that problem. Actually, many teams in my company have moved from Java to Kotlin, and the transition was really smooth. Like the Kotlin works very well with the Java ecosystem, and I think that if you don't want to change the paradigm, but you would like to have a language with a better syntax, then there's no problem with going from Java to Kotlin. But of course, if you'd like to change the paradigm, then yeah, Scala is the answer. So the things that might be taken from outside to Scala.
Yes.
Oh, yeah, I think that that's a tough one, I would say. I think that after exploring some Kotlin in detail, maybe Scala could adapt maybe some things like the way it's, for example, in Kotlin, it's much easier to express extension function than in the Scala. I know that this will be solved in some way in Dotty and Scala 3, but the current syntax for like extension functions and having to go through implicit classes, it's like a problem, to be honest. And I hope that maybe Scala will just look into other languages and find its own way to provide a simple solution to having extension functions. I'm also like, what was interesting outside Scala, but still on the JVM, I think that coroutines are quite interesting. Maybe Scala could look into coroutines in Kotlin, and maybe should or could make some its own solution that will work as a coroutines. But we already have like Monix, Zio, and that's Katz effect, so I'm not sure it's really that worth giving a try.
Yeah,
thank you. Thank you.
Bye.
Bye bye.
Thank you. Bye.
Thank you. Thank you, guys.
Thank you very much.
Thank you. Thank you. Bye bye.
Bye bye.